Happy Friday, everyone. It's the Friday before Martin Luther King weekend, and I hope you guys have a wonderful time. Hope you guys take a moment to reflect Martin Luther King and everything that he's done for this nation. And yes, it's a day off of school, but that doesn't mean we shouldn't acknowledge what he did for us. He was an awesome civil rights leader. So anyways, here we go. Still working on exponential functions. Specifically, today we're going to be talking about exponential growth. And again, I'm using some big pen, so I'll probably be reading a lot of what I wrote. That does say exponential growth. All right, so exponential growth, and I'm going to abbreviate this. So my kids, remember this vocab. Exponential growth. Vocab. Remember, it's pink. Now, exponential growth occurs when a quantity or something that you're talking about increases by the same factor over the same amount of time. Okay? So it's a quantity that increases as in changes and grows larger, not increases as in adding. It increases by the same factor over equal amounts of time. I have Peter Pan ears on, by the way, because I'm thinking of the happiest things. Peter Pan. There you go, exponential growth. A quantity that increases by the same factor over equal amounts of time. Remember that factor is what we're looking for, that it has to be the same between each data point, I guess you'd say. And with exponential growth, we have an exponential growth function. Exponential growth function, which is, there's a whole lot of letters in this. Y equals A times quantity 1 plus R to the T power. A is your initial amount. Yep, they're still calling it that. A is initial amount. Initial amount is also known as what's it starting at, kind of a thing. Which one do we want to do next? R is your growth rate. So how this quantity is changing as a decimal. Okay, so they are going to give it to you as a decimal, but you need to change it into a percent. So maybe I should actually. No, that's fine. That's fine. T stands for time. And the 1 plus R, that is your growth factor. And then Y is your total. Y is total amount. So when you're done with all this, that guy's pink, that guy's blue. This is what we're going to focus on today. So remember, A is the initial amount. That's what you start out with. Y is going to be your total amount after you have your growth in there, your growth factor and all that, and the time. You can hit pause. I don't know why I'm waiting. You can hit pause. Okay, so I'm going to erase that. I'm going to put my function at the top. Y equals A times quantity 1 plus R to the T power. So I have that thing going. So we have that always easily to look at. And now we have example 1. Okay, so it says the function Y equals 150,000 times quantity 1.1 to the T. So this function represents the attendance Y at a music festival T years after 2010. Okay, so Y is the attendance. Remember, I always write down any information that's given to me. And then T is years after 2010. Information they give us the problem. Here's the function. Y we know is the attendance, and T is going to be the years after 2010. And part A says, what percent does the festival attendance increase each year? So how much is it increasing? So we're going to use our growth factor here. So if it's the growth factor is equal to 1.1, you are going to set it as 1 plus R equals 1.1. Because this is what we're trying to figure out. We're trying to figure out how much it's growing, how much it's changing. And so you're going to use your growth factor there. And that is the amount afterwards. So you're going to start with what it is beforehand. And then you just have a little baby equation to solve, minus 1. Remember, when you subtract 1, you're subtracting the whole. So R equals 0.1. So that tells you your rate, your growth rate is 0.1. What does that mean? Well, turn it into turn your decimal into a percent. Sorry about that. So your growth rate is actually 10%. So it's growing 10% each year. All right. Now on B, what they're going to do is they're going to ask us how many people will attend the festival in 2014. So how many people in 2014? So exponential growth is good for predictions as well. If you are trying to predict, like this problem is, how many people they're going to get a bunch of years if you know certain back years data, kind of a thing. And then it says round your answer to the nearest 10,000. Wow. Round to nearest 10K. I'm running out of room. Okay. So now what we're going to do, we've got to figure out the difference between 2014 and 2000. It started with 2010. Oh, there it is. 2010. So our T is actually going to be 4. Okay. And then we're going to go up to this function. Y equals 150,000 times the quantity 1.1 to the 4th power. So we're going to substitute T as 4. And all I did, I found the difference between 2010 and 2014. You need to have your calculator. I forgot to tell you that in the very beginning. So we're rounding the nearest 10,000. You've got to remember your order of operations. Do not multiply this first. No. You got to take 1.1 and raise that to the 4th power first. So 1.1 to the 4th. Oh, there we go. So 1.4641 is what it looks like. Yes. Keep this in the calculator. So we have 150,000 times 1.4641. Keep that number in the calculator. And then, on your calculator, multiply this by 150,000. And you get that big number, and we're going to round it to the nearest 10,000. Okay? So that is actually 219,615. But we're rounding to the nearest 10,000. So that's the number we're rounding it to. Okay, nope, sorry, my line's underneath the wrong number. There we go. So we're going to look at the 9, and the 9 is going to push that one up. So our answer is approximately 220,000. But what? You got to make sure you have a label. People. So there's going to be approximately 220,000 people at the music festival in 2014. So on your growth rates, make sure you turn your percents into a decimal. Your rate is going to be listed as a decimal form, but when you use it in your final answer, you want to change that over to a percentage. So exponential growth, it's just about finding your growth rate and then your growth factor, and then basically multiply it by how long it's going to be, whether it's months or years. I've always seen most problems in years. I haven't really seen many problems in months. You can. There's not much to it. All right. Now the next part of exponential growth, we're going to be talking about compound interest, which may seem silly. You're like, wait a minute, why are we talking about money if we're talking about exponential growth? You'll see why in a second here. And in Math 8, you learn about, no, is it Math 8? 7th grade. You learn about interest, basic interest. Interest, I equals PRT, principal times rate times time. That's just your simple interest. Compound interest is a little bit different. Here's your formula. This is a good one. So the difference between compound interest and simple interest. Compound interest, you pay money on the principal, which is P here, which is what you're borrowing. So, if you want to borrow $1,000, your principal is $1,000. So I'm going to pay interest on that, and I'm also paying interest on the interest that's already occurring. So it's like you're paying double interest. But most things are compound interest. Houses are, I think. I'm not quite sure on that. Okay, so let's talk about compound interest, this formula, how you calculate it. P is your principal amount. PAL, principal amount. R is rate. And actually it's annual. Annual rate as a decimal. Annual rate is decimal. We're going to turn that decimal into a percentage. You always end up doing that. N is the number of times it is compounded. Number of times interest is compounded. T is time. In years. I think I got them all. NP, PRTN. Yep. Looks good. So this one, even though it looks kind of big and gnarly, it's just plugging the numbers in and taking your time and making sure that you do your order of operations properly. By the way, that's blue, my kids. Okay, so example 2. So when it says N in this compound interest, number of times interest is compounded, interest can be compounded like 4 times a year. That's, how many times you're going to get charged interest on the interest. I believe that's correct. Yes. Okay. Example 2. Here it is. So you're going to write the function. Problem says, you deposit $100 in a savings account that earns 5% annual interest compounded yearly. So that means one time. Write a function for the balance after T years. Okay. So we have P is $100. That's how much you're talking about. That's your principal. Earns rate is 5% annual. And it's compounded yearly. So N, that's going to be N. Number of times it's interest compounded yearly. So N is 1. It's going to be compounded yearly, meaning 1 time a year. And we're going to write a function for the balance after T years. So we're just going to plug this stuff all in up here. Write a function. Write a function. Here we go. Oops, y equals. I don't know why I started with P. Y equals, our principal is 100, times quantity 1 plus R, our rate, 5%. Remember, we want that as a decimal. So 5%. If I put 0.5, remove it, that's 50%. So it's 0.05 over N, number of times it's compounded in a year, which is 1. And we're going to raise that to the NT. So time in years, it's going to be, oh, it said 1 year. Oh, but the balance is after T years. Pardon me. So T is just T. And then N is number of times. So it's times 1. 1t, because that's what we're supposed to be writing. We're trying to figure out what t is. And so on this, simplify the parentheses first. So we have y equals 100 times quantity 1 plus 0.05 divided by 1 is still 0.05. To the 1 times t, well, 1 times t is t. And I'm running out of room. Simplify this. So 1 plus basically a nickel. So 100 times 1.05 to the t power. And then you're done, because you're just going to write the function with this given information. And that, I forgot to circle my y over here. And that's your final answer. Sorry to see, guys. Y equals 100 times the quantity 1.05 to the t power. So we're just substituting the numbers in and writing our function. And then from there, you would be able to write up. You'd be able to solve a problem based on, whatever they want to say. I don't know. I can't think of anything off the top of my head. It's Friday. It's been a long week. Okay, so I am going to erase that. I'm going to keep my compound interest. Now let's do example 3. And this is real life. All right, table shows the balance of a money market account over time. Okay, so I'm gonna draw the table. So x, y, 0 through 5. 1, 0, 1, 2, 3, 4, 5. I'm just doing an input output. And then 100, 110, 121, 133.10, 146.41, and 161.05. And X is, technically this is your year T, and Y is your balance. Part A. Write a function for the table. So let's go over this part. P, which is our initial principal, our starting amount, we do have that. That's going to be when X is 0. R, remember, is your rate. We're going to have to figure that out. The number of times it's compounded. Oh, wait a minute. We're not doing compound interest. Hey, brain fart. This is exponential growth. It didn't say anything about compound interest. I think I just had compound interest in my head. So y equals a times quantity 1 plus r to the t. That's the function we're working with. Sorry, I thought it was still part of the compound interest problem. The light is changing. Okay. Now I'm back ready to go. So we do have A, which is our initial amount, which is 100. Our rate, that's what we have to figure out. So we've got to find the change in Y. Okay? And so basically you're going to go 100x equals 110. Or you can just go 110 divided by 100. 110 divided by 100, which is 1.1. So this is being multiplied by 1.1. Let's see if that works for 110 to 121. So 110 times 1.1. Aha! It is 1.1. Let's just double check. So 121 times 1.1. Yep. So now we have figured out our rate at which it's changing. Okay. So if we multiply this by 1.1, we got to figure out what the actual rate is. Like, how much is it increasing? Is it increasing 110%? No, it's only increasing 10%, because the difference between 100 and 110, it's only 10. And 10 is actually 10% of 100. So our R for this problem is actually 0.1. You gotta think of, you gotta be careful about what you're looking at for your r. So here we go. Y equals a times quantity 1 plus r to the t power. So y equals a, our initial amount is 100, times quantity 1 plus, remember this is going to be 0.1 because it increases 10%. 10% of 100 is 10. 10 added to 100 is 110. That's why your rate is 10%. So 1 plus 0.1. Simplify this. 100 to the 1 times 1 plus 0.1 is 1.1 to the t. And you just wrote your function for this. Be careful about this because you got to remember what you're asking. How much is it increasing? What's the rate at which y is changing? And it's changing by 10%. But here you're just figuring out what the common factor is. Your common factor is not your rate. Be careful. Part B. It says graph the function. Meh. You guys know. You guys can graph all those points. Oh wow, and that's it. Part B just said graph. So you'd plot x and plot y, and there you have it. And you would see that this is not a line because this is not linear. Okay. Boy, that was it. Sorry for the confusion on the compound interest. I thought it was still part of that problem. Then I realized, wait a minute, this isn't interest. This is exponential growth. Not my finest video, girls, kids, boys, girls, whoever's watching this. But it happens. It's Friday at like almost 4 o'clock. It's been a long week. I hope you guys have a great week. I hope you think of the happiest things. Have a great weekend. I'm out.